All right, hello. Today's lecture will be the first in a series of lectures on gases and gas laws. And there can be no doubt of the importance of gases to life on Earth, whether it be oxygen that is responsible for respiration, or whether it be carbon dioxide that is responsible, one of the gases responsible for photosynthesis. And in addition to that, as humans, we use gases and properties of gases to our advantage. So let's begin. There's going to be 7 laws. All I'm going to do right now is mention them. You're not going to remember them right off the bat, but you will become very familiar with Boyle's Law, Charles' Law, Gay-Lussacs Law, combined gas laws, ideal gas laws, Dalton's Law, and Graham's Law. Ultimately, you will use those laws to help explain the characteristics of gases, and you will use the math involved with those laws not as a punishment, as a tool to help define what is happening, or what is being explained by that law. Let's continue. Let's begin today with properties of gases. Some very unique and interesting properties. Okay, number 1. And we're just going to read these because we're going to talk about them within the lecture. Gases can be compressed. Number 2, gases can expand when less pressure is applied. Number 3, gases can be mixed. Think about the atmosphere, one of the most important mixtures of gases that we could probably think of. Number 4, gases exert a constant pressure on their container walls. And number 5, gases have, by the way that they're put together, they have very low densities. All right? Remember STP. You remember back when we were studying about the mole, all right, the number of representative particles in a substance, that we were introduced to something called Avogadro's hypotheses. You remember that in Avogadro's hypotheses, it was stressed that we need to sometimes consider gases in an apples to apples comparison. Therefore, we talk about STP. What is STP? It is standard temperature and pressure. In other words, keeping variables the same so that we can have a fair comparison. And we learned that if we were looking at STP, 1 mole of any gas would occupy a volume of 22.4 liters. Now, so what we're assuming is if we have 3 balloons that all have the same volume, if they are at STP, they will also have the same number of molecules inside of them. Okay, and I want to remind you of that because you previously learned that. So that would be a characteristic of gases. I also want to remind you of this because you've seen this before. You know that when you are looking at solids, the atoms in that are very tightly packed. In fact, there's very little flexibility. It's very rigid, very dense. You know that liquids are also fairly dense, but these molecules or atoms have the ability to move around one another, and so the liquids have the ability to flow. You know that gases are the least of all. In other words, they're not very tightly packed together. These molecules have a great deal of kinetic energy, which is energy in motion. Therefore, they can be compressed, but they can also expand. This sort of, when you start thinking about this, and I'm not advocating that anyone smoke, but most people have at some point in their life been around somebody maybe smoking a pipe, particularly a pipe because of the you can really smell it. So my question is, what is the ultimate volume of a gas? I mean, think about this. You can be pretty far away from someone, okay? You can be pretty far away from someone and smell or get, some of those molecules of that gas that are expanding out, really expanding. So what is the ultimate volume of a gas? Which kind of makes gases different. Okay, this is what this is about right now, characteristics. So it makes gases different from a solid or a liquid. Okay? All right, now what I want to share with you next are some facts that related to the kinetic molecular theory of gases. The kinetic molecular theory of gases. Okay, number 1, we consider gases to move in straight line paths, okay? And we consider that as they're moving in those straight line paths, that those molecules are in constant motion. Number two, we consider gases to be widely spaced. Well, we've already covered that, okay? Number three, we consider that gases collide with each other, okay? So molecules could hit each other, and they can also hit their container walls without really losing their kinetic energy. Okay, what keeps a balloon inflated? All right, number four, we consider gases to move more as individual entities, more as individual particles. And the attraction between them, honestly, is negligible. All right? All right, I want you to consider this, because I want you to consider there's always a practical side of science. Here's a practical side of understanding gas laws. And in this case, the idea that a gas could be compressed. You have a crash car dummy, probably moving at a high rate of speed, hitting a fairly immovable object, and the airbag deploys. This dummy hits, and what if this were a real person in real life, hits this airbag, but the airbag, by the virtue of having a gas in it, has some compressibility. Well, there's a lot of physics here that we're not going to talk about, like the transfer of momentum, like force, like inertia. There's a lot of things we're not going to talk about, but I'm going to tell you, I think we all realize that this, having the ability to compress and absorb some of that impact and soften some of that impact, would be a characteristic of gases that we would very much put to our advantage that might literally save someone's life. Okay? Now, you're going to eventually get into the 7 gas laws. And when you do, I figure you're already, you're smart enough to know there's going to be some equations. This is inorganic chemistry. There's a lot of equations. So you're going to say, okay, so these equations are going to have symbols, or they're going to have variables. Yes, there are 4 variables that tend to be used to describe what's taking place with gases. Like, for instance, pressure is a capital P, and case is important. Volume is a capital V. Temperature is a capital T, and the amount of the gas is given with a lowercase n. However, when we say amount of gas, we're really also talking about the number of moles. So these 4 variables will be very important to you when you begin to use the gas laws and the arithmetic to explain the characteristics of gases. Okay? All right, now here's a question. And I know you say, well, it seems like it's too simplified of a question, but no, there's really science of gases going on here. How does this work? And I don't mean just taking your hand and pumping it up and down. I mean, what are you really doing when you inflate a tire? You are pushing this down, which pushes the gases in this barrel into the tire, but what are you doing inside of that tire? Well, you're literally increasing the amount of gas that's in that tire. So you're increasing the likelihood of a gas-to-gas collision. You're increasing the likelihood of a gas molecule's collision with the side of its container. And so what are you doing? You're inflating the tire, but what are you really doing? You're increasing the pressure, okay? So we're using a characteristic of a gas to our advantage. What are you doing here with a vacuum sealed container? Well, it's kind of interesting because you're you're doing something that it's kind of the opposite of the tire. And you have this container with this attachment here, and with this, and you attach this, and you literally are pulling air out of this container. Now, we could get into why that's important to helping keep food fresh, but that's not my concern right now. My concern is, what are we doing with a vacuum seal? We're creating a situation where the pressure outside the container is actually greater than the pressure inside the container. That's why when you take it and you open it, you hear that whoosh. That whoosh is not air coming out in this case. That whoosh is air coming in. Now that would be exactly the opposite of this. What are we doing with this aerosol can? Well, you obviously realize we would want the pressure to be greater inside of the can than outside of the can, because we want the contents of the can to come out. So we are using characteristics of gases, we're using the chemistry of gases, we're using pressure, we're using volume, okay, to our advantage. Maybe that's what science is all about, okay? All right, now can this woman overinflate this balloon? Can she put so much pressure in this balloon that the balloon itself will no longer have the elasticity to handle that? And you know that the answer to that is yes. You can overinflate this balloon for sure, okay? So you can create a situation where the container can no longer handle the pressure of the gas inside of it, which takes me to this. Now, this also gives me a quick opportunity to mention another very fascinating attribute of gases. If you put a gas under enough pressure, you can turn a gas to a liquid. And I don't know how many people understand this and how many people don't, but this propane tank, what's inside of that tank is a liquid. All right, but when that liquid begins to come out of the tank, it goes from that high pressure to a much lower pressure, and when it comes out, therefore it turns back into a gas. So yes, when you're using your grill, you're burning a gas, but as it exists in the tank, okay, it is a liquid, and I understand that. But I still want to ask the question, do I have to have a flexible container to hold a gas? And the answer would be no. No, I don't have to have a flexible container, all right? And then the next question is, thinking about like these propane tanks, why do you only fill it to 80% capacity? You know, why don't you just fill the whole darn thing up? Why do you only fill it to 80% capacity? And we'll come back to that answer here in a moment, okay? To that question here in a moment. All right, next. Let's assume we have two containers. Now you're gonna have to listen to me, because you remember something, you know, we are manipulating items when we talk about gases. So we might manipulate volume, or we might manipulate pressure, or whatever the case may be. So just stick with me here. So let's assume that both of these start right here, and they both have the same volume of gas in them. Okay, they both have the same volume, but all of a sudden, I push this one down, so I decrease the volume. Okay? Now let's also assume that I don't change the temperature, remember, and I don't change the atmospheric pressure. Okay, remember, I want to have an apples to apples comparison. So all I'm doing, same volume, is decreasing the volume. What will I do to the pressure? And I think you already know. I will make the pressure go what? I will make it go up. But why do I make it go up? Because I'm increasing the molecule to molecule, you know, interactions, and I'm increasing the molecule to sides of the container interaction. Pressure goes up. That's an interesting fact of a gas. Now, what's another interesting fact? Well, you know, we keep saying STP, we keep saying let's keep as variables the same, because what if I did increase the temperature? And this takes me right back to a question that I asked earlier. What will temperature do to the average kinetic energy of particles? It will make it go what? It'll make it go up. Is it possible that I could create a dangerous situation with some of these tanks if I overfilled them and then allowed them to get really, really hot? And the answer is yes. It doesn't matter if it's an inflexible container or not. In fact, that might make it even worse. I don't know. Okay? So temperature would obviously have a big impact on, and I know in this case it's a liquid, but we're also talking about gases. Temperature would have a big impact on gases. Okay? All right, so we've discussed a few really cool properties of gases. And we've discussed some properties that we use to our advantage. Now, let's just briefly reach our hand out and shake hands with each of the 7 laws. That's really all we're going to have time for today. you might, here's what I would recommend. I would recommend every time I throw up a definition slide, I would recommend you hit pause. I would recommend you look at it, read it, think about it for a second or two, and then listen to me. And then you'll go back through it with me again when you do the assessment over the lecture. Here we go. 7 people we have to introduce ourselves to. Let's go quickly. All right, number 1, Boyle's Law. For a given mass of gas at constant temperature, in other words, the temperature is not changing, the volume of the gas varies inversely with pressure. Now you got to read that again. For a given mass of gas at constant temperature, so you're not doing anything to the temperature, the volume of the gas will vary what? Inversely with pressure. So what are we really telling you? We're telling you that we have our 2 containers. What are we telling you? We're telling you that we start out with the same volume, but we shrink the volume of one while we leave the volume of the other one the same. But what are we not going to do? We're not going to increase the external temperature or internal temperature, yes? So what will happen? What will happen is pressure will go up. Number 2, Charles' Law. The volume, and we're considering volume, of a fixed mass of gas is directly proportional to its temperature if the pressure is kept constant. Okay, now you're going to have to think about this, and you're going to have to be willing to kind of use your brain and kind of see the big picture. Come on, if you increase the temperature on something, you obviously are going to impact its pressure. So it doesn't seem to make sense when you just first look at it. You're like, if the pressure is kept constant, how are you going to keep the pressure constant if you increase the temperature? Well, you're not. So what are they really saying? They're saying you can't do anything to change the pressure. So in other words, you can't shrink the size of the container. Okay, so you have to keep everything the same. You have to keep everything the same, and then we'll see what temperature does to the volume. The temperature will no doubt have an effect on the volume, but you can't have an effect on the pressure by like shrinking the size of the container or something like that. You have to keep everything the same, and then let's see what temperature does to the volume. And honestly, here's what it does. As temperature goes up, okay, volume will also go up. Now that's assuming you don't mess with anything else, right? Apples to apples, keep all the variables the same, okay? All right, number 3, Gay-Lussacs Law. The pressure of a gas is directly proportional to the temperature if the volume remains constant. Okay, now you're thinking, wasn't that kind of like no, because a while ago it was volume related to temperature. Now we're looking at pressure related to temperature. But what do you mean if the volume remains constant? I thought the volume, okay, once again, this is saying that you are not influencing the volume by like adding more gas or letting some of the gas out, okay? You're keeping everything the same, but you're looking at the pressure related to temperature. And what do you find? This one's pretty simple. You find that as temperature goes up, pressure also goes up. Now there will be equations for all of these laws to explain. Right now we're just introducing ourselves to the law or the idea behind the law. Number 4, the combined gas law. Okay, the combined gas law is relating pressure, volume, and temperature if you keep the amount of gas constant. I mean, think about this. You've got all of these things, amount, pressure, volume, temperature, all of these items impact a gas. The combined gas law is going to relate pressure, volume, and temperature, okay, if you keep the amount constant. Now, this is the one where I started throwing in some equations on you. Not because I wanted to intimidate you, but because I want you to know that you're going to have to use some equations. And I don't want you to be intimidated. If you understand the purpose of the equation, you'll ultimately understand the equation. The combined gas law is relating all of these things together. Number 5, how about the ideal gas law? Okay, you're going to calculate in the ideal gas law, you're going to calculate the amount of gas, when pressure, volume, and temperature are specified. So in other words, if I give you information about pressure, volume, and temperature, with the ideal gas law, you're going to calculate the amount of gas. Number 6. Number 6 is Dalton's law. Dalton's law deals with pressures, okay? Total pressure of a gas is related to all of the partial pressures of the gas mixture. Therefore, total pressure is the sum of all the partial pressures. Listen, don't be intimidated by that. If this canister is air as we know it, you know that air as we know it is made up of more than one type of gas, okay? So if this is a certain proportion of this, and this has a certain pressure, then how much of this does this represent? Okay? So in other words, if you know how much pressure is here, 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 and here, that will tell you how much pressure you have here, because this is a sum total of all of these. And then last but not least is Graham's law. And Graham's law will be the effects of molar mass, and you understand molar mass, on the rate of diffusion / effusion. What's the difference between the two? Diffusion is when all the gases mix together. So what kind of rate? How long does that take? You know, what information about these gases, how, mixing together? Whereas effusion is the rate in which this gas escapes from here into here. So effusion is going from here to here, that rate. Diffusion is how long does it take for you to mix. Now, what have we done today? We've introduced you to some facts about gases, some really cool facts that we use to our advantage. I've introduced you very briefly, you just shook hands, that's all you did, with 7 laws. Are you going to examine them in the assessment? Sure you are. Are you going to examine questions versus what I've told you? Sure you are. And what are you going to start doing? You're going to start learning about gases, and you're going to start learning about gas laws.